Good evening, everyone. Welcome back to the webinar series on quantum algorithms using Qniverse. Last week, Professor Ramlan Chakrabarti introduced us with quantum Fourier transform and quantum phase estimation algorithms. QFT being an equivalent of classical Fourier transforms, wherein QFT operates directly on quantum amplitudes. QFT performs the transformation exponentially, which we saw in the last seminar, where it was much exponentially faster than classical methods, which is critical for large data sets. QFT is foundation for key algorithms like Shor's algorithm, which we shall see in today's session, which we will learn in today's session. So before we move on to today's session, few announcements. I request the participants for providing a video testimonial about the platform, the Qniverse platform, its usage, capabilities, features, and all those things. So what you earn, you can get first-hand experience of coming to CDAC Bangalore to visit our quantum photonics lab, and also 100 free credits on our Qniverse platform. Many in the past webinars, many participants had asked for reference materials on these. I mean, you can get the reference materials, many reference materials in the Google. I also request today's session speaker Jotishwaran to guide on this if he has any reference materials to provide us. I request him. And regarding the advanced notification about the topics, yes, we share the topics on Monday itself. If the session happens on Wednesday, as today, we share the session details on Monday itself. So there is an ample time of 2 days or 3 days for you to refresh the topics and come prepared for the seminar. Then the session materials, we will upload the session materials as and when the webinar completes on Wednesday, and we'll upload by Thursday. Regarding each webinar sessions, we will have a small quiz wherein we'll ask for some few questions to refresh your learnings of the webinar. And please keep the chat clean and ask only the questions required for the speaker. And we move on to today's session. So today's session is on Shor's algorithm, so which will be delivered by a PhD scholar, Jotishwaran from IIT Roorkee. He is a PhD student from IIT Roorkee with a bachelor's degree in electrical engineering from IIT Jodhpur and a master's degree in physics from IIT Roorkee. He has been part of several courses in quantum computing by CDAC, and we were fortunate to collaborate with him during the QSIM development as well. Now I request Jotishwaran to deliver the lecture. Thank you, Jotishwaran.
Yes, I should be visible, right?
Yes, you are visible.
So, good evening, everyone, and welcome to today's session. Let me first share my screen so that we are. Wait, let it. This thing seems to auto minimize for some reason. Screen 2, share. Yes, so the screen should be visible now. All right. So before I begin the talk, so regarding the question that Santoshji asked, as far as material for studying things go, I'm sure like the slides that we are using will be shared with the attendees, correct?
Yes, the slides will be shared.
Whatever I'm
Yes.
using, I'll be sharing with you. So you're free to share it to them.
Yes, thank you.
Regarding other materials, like as once again Santoshji mentioned, CDAC has had several, online quantum courses. I'm even seeing some familiar names in the chat. So you should know that by now. So you can always go back to those courses and refresh your basics. And I can't speak for the other members, but my session will be pretty self-contained. Whatever you need to know is pretty much presented here. So worst case scenario, you may need to take a term and maybe search online for what it means. But more or less everything that is present, I have defined it here. So whatever we are going to talk about is going to be pretty self-contained. So yeah, minimize this also. Yeah, this way I can see my entire screen. Okay, so let us
Jotishwaran,
begin. Yeah,
once again, we are not able to see your full screen rather than it is in the slide mode,
yeah, because I
the
will be
normal.
writing also here, so I cannot use the
Oh,
presentation.
okay, fine.
Yeah,
Okay,
so I will
yeah,
be using the draw function of PowerPoint. So I'm not using
okay,
like in the presentation mode. I cannot do that. I don't have a touch
okay, fine.
screen, unfortunately.
Yeah, okay, okay,
So
fine. Please go ahead.
yeah, so all right. So the title of my talk today is the RSA Cryptosystem and Shor's factoring algorithm. So Shor's factoring algorithm, as many of you may know, is an algorithm that allows us to factor integers. It allows us to factor integers in polynomial time. So that is the premise of the algorithm. Now, why do we need an algorithm for factoring integers? What is the use of it? There are many, many ways to explain that. But what I personally find is that it is best to take the most immediate application, see what is happening in that problem, and then motivate the reason for Shor's algorithm. And additionally, I would also like to address some general points about quantum algorithms while covering the topics of today's talk. So for the most part of today's session, for half an hour or maybe more, we'll be talking about the RSA crypto system. Many of you in the audience may know this, so kindly bear with me. For those of you who do not know, this should serve as a reasonably good enough introduction. I'm not going into too much details about anything. Nothing mentioned here is inaccurate per se, but again, nothing mentioned here is complete also. So you are encouraged to go do your own reading after this session. So first, very briefly, a glossary of terms. This may be very elementary, but nonetheless, I'm presenting it. A prime number is a natural number p that is only divisible by 1 and itself. Any number that is not prime, we will call a composite number. So this is the very basics of the number system. So we can then define what is known as the GCD, greatest common divisor of two natural numbers. So can I just remove the grids? I would need the grids for writing because it helps me maintain a straight line. But okay, let me just turn it off for now. When I start writing, I will get it back again. So that should be in. Wait, where is that option? I forgot. Oh, not here. View. Yes, grid lines. Turn it off. Yeah. Yes, this should be fine now. But when I start writing, I will again turn them on. Okay. So the GCD for two numbers is defined as the largest number that can divide both P and Q. Here, division is defined in the standard school book sense. So when I say a number A divides a number B, I mean that A can be written as, B can be written as some K times A, where K is an integer. Or in other words, I can say that the remainder after division is 0. The remainder is also known as this quantity modulo. So for example, I can say 5 mod 2. When I divide 5 by 2, I will get a remainder of 1. When I divide 13 by 5, I will get a remainder 3. Now, the curious observation here is if I choose a base for my modulo, say 2 or 5 or whatever, we can see that I can assign a modulo value to every single natural number, or rather every single integer. So what I'm doing is I'm creating a mapping between the set of integers and the set of the numbers modulo n. So if I'm considering modulo n, when I'm dividing a number by a natural number n, the remainder can take values 0 to n minus 1. Because if it is greater than n, then I'm just adding 1 to my quotient. So it is always going to be between 0 to n minus 1. So what are we doing by considering the modulus? What we are doing is, like, this is the basis for modular arithmetic. all natural numbers, or so to speak, all integers are mapped into n distinct equivalence classes based on what remainder they leave behind when divided by the number n. N is any natural number. Technically speaking, it can be any integer, but for today's purposes, it is fine if n is a natural number. Okay, so when I say A is congruent, so over here I use the equality sign. So here I mean I'm literally evaluating the remainder. But when I write this, when I say A is congruent to B mod n, what do I mean? I mean A can be represented as m times n plus b, where m is an integer and b is an integer which is between 0 and n minus 1, n minus 1 included, or I can say less than n where n is not included. So this is what we call congruence classes of the modulus. So when I have these congruence classes, essentially many integers will fall into the same class. In fact, if I'm considering all integers, infinitely many numbers will be mapped to this finite set of n values, 0 to n minus 1. So once we get the modulus, we can perform arithmetic with them. So if I say A is congruent to B mod n, then A plus K will be congruent to B plus K mod n. K times A will be congruent to K times B mod n. A to the power K will be congruent to B to the power K mod n. So these are standard rules that you can verify by hand, or you can just take it for granted. So these are the basic rules, mathematical rules that we shall be using for today's discussion. So again, all these rules are allowed for any integer a and b and any natural number k. Because of the last rule, k cannot be negative. So, but for the other two rules, k can be negative. But since I'm considering all three together, I'm saying k is a natural number. And if n divides a, then a will always be congruent to 0 mod n. So this is the definition. If a is congruent to 0 mod n, then a is a multiple of n. Like if I write the multiplication table of n, somewhere in there, the number a will be present. I can't say where, but I know it is present in the table. So I can put it in that class. So that is the congruence class 0 mod n. Okay. Now let us move on to the RSA cryptosystem. So what is the RSA cryptosystem? Right now, I'm just describing it as a mathematics problem, as a mathematical problem. We don't have the time to go into all the details of public key cryptosystems and what they are used for, how we can use them. I'll just present this as a simple mathematics problem. So let P and Q be two prime numbers. The slides should be shared to you, you'll get it, don't worry. So let me take two prime numbers, P and Q. P and Q are prime, so P and Q have no other factors other than 1 and themselves, and I construct the number n as P times Q. Then I compute this number called lambda n. Lambda of n is given by LCM of P minus 1 and Q minus 1. So LCM, yes, this is one thing I should have included in the glossary. I did not include it. So let me quickly make a side note here. LCM is the least common multiple. So it is kind of the complementary concept to GCD, where this is the smallest number such that both the individual numbers P minus 1 and Q minus 1 divide it. Okay, so that is the LCM. So then what we do is, so this is step 1 of the RSA crypto system where we are generating the key. So first I need two prime numbers. Then I compute this value lambda n. Then I choose a number e, which is between 1 and lambda n, such that GCD of e and lambda is 1. So when GCD of two numbers is 1, they are co-prime. Essentially, they do not share any factors between the two of them. So, and of course, I cannot choose 1 because 1 is the trivial value and it does not allow, it's a very poor choice. So it has to be greater than 1. It has to be less than lambda n. Typically, they choose a prime number inside this. So by virtue of it being prime, it will have a GCD of 1 with lambda n, whatever the value of lambda n is. Then we will calculate d, the number d, such that e multiplied by d is congruent to 1 mod lambda n. So what does this mean? This means, so I will write this right here. So let me quickly turn on the grid lines. I will turn it off once I'm done. So when I say E times D is congruent to 1 mod lambda, what I mean is, again, we can quickly go back. Just use this. If A is congruent to B mod n, then A can be written as m times n plus B. So just going to do that. E times D is going to be m times lambda n, sorry, lambda n plus 1, which implies E times D minus 1 is equal to m times lambda n. Again, lambda n. Essentially, I choose a number D such that E multiplied by D is exactly 1 more than a multiple of lambda n. And it is possible to find this number. Now, this is called the inverse of E modulo n, because the product of these two numbers gives me 1. So although they are individually greater than 1, when I perform modular multiplication modulo lambda n, I get the answer 1. So D is the inverse of E modulo n. Then we have all the keys that we need. N and E are made publicly available. N is known as the RSA number and E is known as the public key. There is usually only one N, but there can be many E's because I can choose many E's over here. So this is typically decided by the sender, but N is a fixed thing. It's a standard number. So I'll talk about that in the end. And then this number D is stored as a secret key. So that is available only with the sender. Nobody else has access to that. Sorry, not the sender, only with the receiver. So this is a public key crypto system where the receiver will put out these informations out in public and say, okay, anybody who wants to securely send me a message can use this method. And anybody using this public key crypto system to send a message will have the confidence that only the person who possesses this secret key D can decrypt their message and read it. Okay. Now, how that is going to happen, we will see in a second. Now, yeah. Then how does one perform an encryption? Remember, the person performing encryption will have only two values with them, N and E. Yeah, let me turn off the grid. Yes. N and E. So what they do is, right now, let me assume all messages are numbers. There is a method to convert any message into a number. I'm not going into it. Right now, I just want to transmit a secret number. So let there be a number M. So the number is encrypted using the following, by evaluating the following quantity. I evaluate C, which is M raised to the power E mod n. So I take the exponent of the public key, like I take the Eth order exponent of M and take the modulus with respect to n. That number is C. Now, since I'm doing mod n, I know C lies between 0 and n minus 1. So there is that number. And this C is the ciphertext. This is the secret. Now, if only C is known, or if only C, N, and D are known, one cannot find out what the value of M was, because all they know is C is some multiple times, M to the power E is some multiple of N plus C. Now, what multiple it is, we don't know. So we cannot directly invert this function. So for people who are curious about cryptography in general, such functions are known as one-way functions. Essentially, it's very easy to evaluate this function, but it is almost impossible to evaluate the inverse of the function. Or it is possible to make the inverse evaluation impossible by hiding certain values. Here, by hiding certain values, we are making this impossible. So this is direct inversion and impossibility. So these functions are called one-way functions. So these are of great interest to cryptographers in designing very many primitives. So people who are seriously studying cryptography will come across these one-way functions, in the course of their study. Now the ciphertext C is prepared. Now, how does the receiver get M from C? What they do is they perform the following operation. They perform C to the power E. Sorry, oh my God, I made a mistake. It's not C to the power E, it is C to the power D. Yes, yeah. Because D is the secret key. Yes, I think. Yeah, let me change it in real time. Yes, secret key D. Yes. So whatever ciphertext they receive, they take the modular exponent to the order D, take the modulus, and we are guaranteed that it is going to be M. Well, why are we guaranteed it is going to be M? For that, the following things need to be satisfied. First and foremost, M should be a number less than N. It should be, it can be 0, but typically nobody is going to share the number 0, because if I chose 0, every number in this process is going to be 0. Okay, so usually 0 is going to be a poor choice. So M or any number congruent to 0 mod n is going to be a poor choice. So it is between 0 and n. And additionally, P and Q should not be very small. Like I said, P and Q are prime numbers. Typically, we want these prime numbers to be very large. How large? We'll see in a minute. Like we'll see towards the end. And these prime numbers, so there are algorithms, there are techniques for generating prime numbers, because certain classes of prime numbers we know have certain structure, certain formula. So those numbers are not desirable for RSA. We need prime numbers that are usually found through a random search. So I need very high quality random number generators by which I will randomly generate very large numbers and check them one by one to see if they are prime. So I need to find two such prime numbers, and then I will get my RSA number, which is the product of these prime numbers. This is the reason why the RSA number is usually a global constant. It is just out there. Generating the secret key is entirely, to generate the secret key, that is entirely like on the receiver's end. Okay, so yeah, all right. So that does this. Now, why does RSA work? Why does this method work? So far, I didn't tell you why this works. I just told you this happens. The reason this works is essentially due to a fundamental property of numbers. If, say, I have a number a and n, and if I try to evaluate this function, f sub a of x, which is defined as a to the power x mod n, this is a periodic function for all natural numbers a n and r x. So as I keep varying x, the function will start repeating its values. What are those values? I don't know, but I can expect this to be periodic. And that is just how numbers are. Like I can go into the details and explain why that is the case, but for now you can take it as a given. Now, if a and n are co-prime, that is, if GCD of a and n is 1, then there exist particular values of r such that a to the power r is congruent to 1 mod n. Essentially, if I evaluate a to the power r mod n, I will get the answer 1. So if a and n are co-prime, individually they can be composite numbers. But if a and n are co-prime, there will always exist many values r such that a to the power r is congruent to 1 mod n. Essentially, like, let me again clarify this here. What do I mean when I say this? I mean a to the power r is equal to m times n plus 1, which implies a to the power r minus 1 is a multiple of n. Okay. As long as a is co-prime to n, we can get such numbers. So this is a consequence of Euler's theorem. Where is my, yeah. So this is a consequence of Euler's theorem. More precisely, it is a result of a refined version of Euler's theorem, but Euler's theorem is the starting point for this. Well, technically, Fermat's little theorem is the starting point for it, but you can look up this Euler's theorem to understand why this is the case. Okay, so in this case, when A and N are coprime, the smallest value of R which obeys this property, essentially the smallest possible value of R for which I can get this relation, is the period of fa of x. So when A and N are coprime, the smallest possible value of R such that this happens yeah, I just saw a question. So that was okay. So yes, a to the power r mod n is 1. Yeah. So that is what I mean here. So since the remainder when dividing a to the power r by n is 1. So a to the power r can be written as a multiple of n plus 1. So that is the meaning of that. Okay. So is the secret key only D, or can we change the secret key according to any alphabets? Okay, D is not a letter here. Let me quickly go back. D is a number. It is a number such that this holds. Okay, E times D should be n times lambda n plus 1. D is a number. For a given E, you can find a D. Okay, E will determine what D is. All right, so back. Yeah. Oh, no. I skipped one slide ahead. Yes. So R, the smallest value of R is the period of the exponential function, because you can guess. If we can quickly go back to the glossary, see, any multiplication. So if I have a to the power r here and I multiply one more a to it, what is going to happen? A to the power r mod n is 1. If I multiply another a to it, it is going to be a times 1 mod n, which is going to be a mod n. So the cycle will begin again. Whenever I hit a to the power r congruent to 1 mod n, I will again start from there and go around until I reach 1 again. So this is a periodic sequence. Okay. Now, once again, I went one slide ahead. In case of RSA, the quantity lambda n that we calculated is the smallest value of R. So that is what lambda n was. So this lambda n is known as the reduced totient function or the Carmichael's totient function. So again, you can look up the underlying term. You'll learn more about what it is. So that is what we calculated. And that is why it is an important number. So once we, without finding lambda n, we cannot proceed to create the secret key. We need lambda n to get the secret key. Okay. So yes. Now, assuming that for now, let me assume that my message M is coprime to N. Let me say GCD of M and N is, oh God, I found out a mistake. It is not M. Think of this as some number K. This is not the message. Yes, I think I understand why one of those questions was asked. This is K times N plus 1. Okay. So, yes. Now C, the ciphertext is M to the power E mod N. Again, to calculate this, I don't need to evaluate M to the power E and then divide by N. There are efficient algorithms to do that also. In fact, there are very simple algorithms where I just need to be able to calculate N square. If I can calculate N square, then I can calculate any M to the power any number mod N. I can do that. Again, since we are short on time, I'm not going into those algorithms. Okay. Now, this is the encryption process. Now, when we are performing the decryption, what are we doing? We are calculating C to the power D mod N. Now, Rishikesh Jadhav, I will come to your question in the end. So if I have, yeah, where was I? Yes. So since E times D is congruent to 1 mod N, I know E times D can be written as K times lambda N plus 1. K is some integer. I don't know what it is. Therefore, what is going to be C to the power D? C to the power D is M to the power E to the power D, which is M to the power E times D, which is M to the power k times lambda n plus 1. So I have m to the power k times lambda n multiplied by m. I can like separate the sum in the exponents as multiplication in the bases. I know this quantity here. Since I know m is the since this is m to the power lambda n, lambda of n, whole raised to the power k. But I know m raised to the power lambda n is congruent to 1 mod k. Because this is a co-prime number and it has to be lambda n. So it is always going to be 1 mod k. So this is 1 to the power k, which is going to be 1. So ultimately the resultant value is m mod n, but I know m is less than n. Now, just if I try to divide any number, if I try to divide a number a by a number larger than a, like if I try to divide 2 by 3, what is the remainder going to be? It is going to be 2 because 2 is smaller than 3. Therefore, no multiple of 3 can be equal to 2. So I'll just have to write it as 0 plus 3, 0 times 3 plus 2. So for any m less than n, I will get the exact value of m. So this is how we, would I explain that? No, I will not. I'm sorry, Shubham. I will not be explaining that because that will take a little bit more time. I will have to go into the Chinese remainder theorem and show why that is the case. As I told you, I'm only going to talk about RSA for the first half an hour. Time is almost up. I have 2 more minutes left. I cannot do that. You can look it up. Any standard cryptography textbook, even the explanation on Wikipedia is pretty good, or you can look up on Stack Exchange. Okay. So I encourage all of you to look at the general case also. Although when RSA was originally proposed, they assumed that if I choose a message at random, it will more or less be co-prime to n. In fact, a very small number of the numbers less than m, less than n, will not be co-prime to n because n has only 2 factors, p and q. So you can actually count the number of factors and the number of numbers that will not be co-prime to it, and that is actually a very small number. So that was the original reasoning. In the subsequent years, people gave a sharper bound to say that yes, that even if I choose a number that is not co-prime, RSA will work, and therefore things are fine. Now, what does it take to break this system? So this is actually pretty good, right? Because see, I have a one-way function. Because if I give you the number c, you can know nothing about m to the power e. And only if I have d, the number d, I can find out what m was. To find d, I need lambda n. But remember, lambda n is not stored anywhere. Lambda n is thrown away. P and q are thrown away. The only numbers that exist in my crypto system are n, e, and d. So with e, d, and n, an external party can know next to nothing. The system is actually pretty airtight. So if I need to break the system, what do I need? The only publicly known parameters are in fact n and d. I can't even know d. D is a secret key. It is hidden. So with the publicly known values, what can I do? Well, first approach to break RSA is, somehow find out the value of d. But we are talking about more, analytical, scientific approaches. Okay, so if I have n and e, what can I do to break RSA? One way is I can try to find lambda of n. Okay, book name I will represent. I will tell you towards the end. Okay, so yeah, so I can try to evaluate this quantity lambda n. But to evaluate this quantity lambda n, I need to know p and q. I need to know the numbers p and q which multiply together and give me n. But if n is very large, finding out this becomes difficult. In fact, for a very long time, this was considered to be perfectly safe, a very safe choice for transmitting information. The RSA crypto system has been used in cryptography for various purposes for near about, I think, a little over 50 years now. So almost 50 years or maybe even more than that. So this is a very old system. It is very reliable in certain measures, and as I will tell towards the end, it has also been what to say, like you can tweak the parameters in such a way that breaking it becomes more and more like incrementally more difficult. So this is actually a pretty robust system until the early 90s when a certain algorithm came around. So that is the Shor's algorithm. So now we are heading towards the Shor's algorithm. So to find lambda n, I need to know P and Q. Find P and Q, I need to be able to factorize the RSA number n. So integer factorization is one thing that I can do to completely break the RSA system. Because if I know the factors of the RSA number n, then game over. Because after that, I can calculate lambda n. Therefore, for any public key, I can find the secret key. All the information is open. So if I can factor n, I am set. Now, integer factorization inherently is not a hard problem. Okay. So in fact, it is, the complexity class of integer factorization is in a very, wishy-washy place. It is sub-exponential, definitely. It does not take exponential time to, yeah, so I will tell what I know about this. So when I say factorization, so first thing is, this is sub-exponential time, classically again. So this is not even an exponential time algorithm. So this is sub-exponential time complexity. And I also know that this is not NP hard in terms of complexity classes. Due to lap of time, I'm not going into what NP hard is. Maybe in the end, if I have some time post questions, I will try to address what these things are very briefly. Okay, it is not an NP hard also. So it's in a very weird place. So from a computational standpoint, this is actually not the ideal choice for a one-way function. But for practical purposes, if I can make sure that to crack my RSA number, to factorize it, it will take someone, 50 years, then for all practical purposes, my crypto system is safe. So that is the approach that was taken way back when RSA was introduced. Now let us consider but remember, the working of RSA is based on very strong structure principles. I have Euler's theorem, I have the Chinese remainder theorem, I have many theorems because of why it works. So the question is, can I use these same theorems to break RSA? The answer is yes. So now I present a strategy for factorizing RSA numbers. So let us consider a toy example, a very basic example. I will take n is equal to 143. People can quickly factorize it in your head. If you want to, please go ahead. And you know what? To mark this, I will quickly switch over to my Qniverse thing. I got logged out. So let me quickly log back in. And let me start the demo. Okay. Not the demo. Let me start a trial run. Let me go to algorithms all the way down to where is Shor's. Yes. No. This is the error correcting code. Simon security. Yeah, Shor's algorithm. Here it is. So let me enter the number 143. Okay. And let me load the circuit. Now you'll find out that the circuit for it is not there. All of these are, like the team at Qniverse has written the code for this. So it can be invoked as a single, call function. So the function has been predefined. So it is here. Now let me try running this. So let me run this on, let me run it on SCP. So let this run in the background. So this is 7218, it's running. So by the time it ends, it should give us some kind of an answer. Okay. So, yeah. Now I'm choosing A as 21. 21 is co-prime to 143. This can be verified. Okay. I mean, these two numbers are very easily factorizable. So it's pretty obvious. So what am I going to do? I am going to evaluate the quantity 21 to the power r mod 143 for different values of r. Now, for r is equal to 1, 21 mod 143 is 21. Then for r equal to 2, I will do 21 squared, which is 441, which is corresponding to 12 mod 143. Okay. So 441, like essentially, if you do, I think 3 times 143, you will get, 3 times 143, you will get 429, which is 12 short of 441. Then if I take the cube, I'm not telling you the number, it corresponds to modulo 109. When I take the fourth power, I get 1. So 21 to the power 4 is congruent to 1 mod 143. Okay. So what does this mean? And as you can see, the cycle begins again. 21, 12, 109, 1 again. Then 21, 12. So it goes on and on and on. Okay. So yes, Nasim, you're right. 3 times 143 is 429. I mentioned that. So I know this. 21 to the power 4 is congruent to 1 mod 143, which implies 21 to the power 4 minus 1 is congruent to 0 mod 143. That is, 21 to the power 4 minus 1 is a multiple of 143. I know this. Now, I just use an algebra trick. This is a to the power 4 minus 1 to the power 4, which alternatively I can write it as 21 squared the whole square minus 1 squared, which can be written as 21 squared minus 1 into 21 squared plus 1. So this, how am I writing this here? Let me quickly make a note. I'm essentially doing, a squared minus b squared is equal to a plus b times a minus b. Okay, now the multiplication of these two numbers gives me a multiple of 143. Okay, so we can quickly check. Now I'm not checking it here, but since this is a very manageable calculation, I encourage you to try it after the session is over. You will find that 143 will not divide either 21 square plus 1 or 21 square minus 1. Both of these numbers are not divisible by 143. What does this mean? I know 143 has only 2 prime factors. Now, the product of these two numbers should have both those prime factors. Is that clear? Because 143, let me take a sidebar and let me turn on the grid. So 143 is equal to 2 numbers p dot q, 2 prime numbers. Now 21 squared, accuracy. So 21 squared plus 1 and 21 squared minus 1. When I multiply both of these, I know I get a number that is some k times 143. So which implies, if I just consider these numbers as their prime factors, all the prime factors of 143 should be present here, which means both p and q should be present inside these numbers. And 143 does not divide 21 square plus 1, it does not divide 21 square minus 1. In fact, this number here is 442, this number here is 440. 21 square is 441. We just saw that before. So this number here is 442. This number here is 440. Both of these are not divisible by 143. So by deduction, by like essentially by just elimination, I know one factor is present in this number, the other factor is present in this number. Like one factor is here, the other factor is here. So one of the factors of 442 is a factor of 143. One of the factors of 440 is a factor of 143. 143 has only 2 factors. So what I do is I take 440 and I evaluate the GCD. It will come out to be 11. Therefore, one factor of 143 is 11. The other, I will just divide 143 by 11 and I will get 13. So this GCD evaluation can be performed by what is called the extended Euclidean algorithm. Again, this is a very nice algorithm. I would have very much liked to go into the details, but we are very short on time. Okay, so please look it up. Please look up the extended Euclidean algorithm. Okay, so and these are standard algorithms. Programmatic implementations of them are available. I'm sure there are, C, C++, Python libraries which already have these pre-established. So you can verify this. So by just taking a number that is co-prime to my RSA number and calculating this table, observing the periodicity, I factorized the number. I didn't do any exhaustive search. I didn't do any of those things. I just got this one expression. Now, what do I need to? Okay, yeah, before that. So this is essentially the logic for Shor's algorithm. Whatever we are going to do in Shor's algorithm is what we just did by hand. So Shor's algorithm is actually just a quantum implementation of a very classical strategy. So this is where I would like to point out that invariably most of the quantum algorithms that you will come across here, that you'll study elsewhere, start from a very classical logic, much like quantum mechanics itself. Like, we start with a very classical description of the system and then we quantize it to get the solutions. We don't do the same thing for quantum algorithms, but the root still exists. So I have a classical strategy with some challenges. Now, what is the challenge? Typically, my RSA numbers are very large. How large are they? So currently we are on RSA. So presently, let me write this here. We are on RSA 2048. RSA 2048, which implies N is a 2048 bit number. Like if I write the binary expansion of N, it has 2048 bits. It is a huge number. So this is a very, very large number. So it is around 2 to the power, like approximately how many digits will it have? It will have something like close to 700. So anywhere between 600 to 700 digits. So this is a very large number and equally, like smaller than N, of course, but equally large prime numbers were used to construct this number. So constructing this table and observing the period is not going to be very straightforward because R is essentially determined by the value of lambda, as I said. Now, what does lambda n? Where does lambda of n come from? Lambda of n comes from lambda of n comes from this. It is LCM of p minus 1 and q minus 1. If p minus 1 and q minus 1 are very large, then lambda of n is going to be very large. It's going to be so large that to manually construct the table will take a lot of time. So the classical attacks that exist to break RSA don't use this strategy. They use a slightly different strategy. Since we are discussing quantum algorithms here, I will not go into that, but I will tell you that it exists. And I'm telling you that for a reason. Okay, so Shor's algorithm leverages quantum parallelism. What is quantum parallelism? Quantum parallelism is essentially the linearity of quantum time evolution. If I have a state psi1 that can be written as a linear combination of two states, phi1 and phi2, essentially if I say get psi can be written as get phi1 plus get phi2, then if I want to apply any unitary transformation to this, it will just linearly spread itself to both the factors. So, and this is the root for quantum parallelism. So this is essentially what I mean by linearity of time evolution, because ultimately all these unitary gates are achieved through time evolving the quantum system. So this quantum parallelism will actually allow me to calculate this table for a large number of values relatively quickly. So now I have the table. I have these values. And the periodicity of the table is going to allow me to find the factor. See, once I saw the periodicity, the strategy is here. I'll just write this number, I will separate them, I will do some minor checks, and then I can get the factors. So what does my quantum computer do in the Shor's algorithm? First and foremost, it creates the table that we created there. It creates a quantum state corresponding to the table. And then you just apply Fourier transform. Now, Fourier transform gives me the periodicity of a sequence. So I need to find the periodicity of this sequence. So I will apply the quantum Fourier transform. So to find the period. And once the period is known, we will use the classical techniques to evaluate the factors. However, it is not as straightforward as I'm mentioning here. There is one small caveat. Yeah, it should be done in another 5-10 minutes. So yeah. So what are the requirements? So first, A needs to be co-prime to N. That is a must. So whenever I'm choosing an A, I need to choose it to be co-prime to N. That can be done relatively easily. Second, the periodicity of my modular exponential function, this R that I find, which is the periodicity of the exponent, it must be even. Because if it is not even, I cannot do this split. The number has to be even to begin with. So if let us say R came out to be 3, then that A is not good enough. I need to throw that A out, choose another A, and then run my Shor's algorithm again. Okay. So this R must be even. And secondly, finally, my factors should distribute them. Remember, the logic that I used is both 442 and 440 do not divide 143. Therefore, each factor is hiding in each of these numbers. That is the primary logic. That is the drive that I had to find out the factors of 143. So similar thing should happen even for that very large number. So this, for 143, it was actually relatively easy because there are like very many good structures for small prime numbers, as I will show you in the toy example. But this will not always happen. So how do I reliably choose an A that is always co-prime? So to do this, what we do is we choose A belonging to this value. We choose A from m squared to 2m squared. Because m squared, of course, is a sorry, I shouldn't write m squared. I should write it as n squared. Oh no. Yeah, I should write it as n squared. Sorry. Yeah, so this is n squared to 2n squared. Because n squared is definitely a multiple of n. It is n times n. What is the next multiple that I will get? The next multiple I will get is, well, it's technically n squared plus n. But within this, like if I go from n squared to 2n squared, there will only be n plus 1 more factors. So between this, I have n squared elements. So this set has n squared elements. With n plus 1 multiples of n. Multiples of n. So, n plus 1 divided by n squared is, 1 by n plus 1 by n squared. So the probability of me finding a number that is a multiple of n becomes very small because n is already very large. So this probability will become smaller and smaller and smaller. So this is a good initial place to choose a name. Why am I stopping here? Why did I choose something like n cube? Because remember, if n has 2048 bits, n squared will have double that. So the number of bits I need to represent the numbers will also become larger and larger and large. So I need to keep that small because ultimately, when I want to move to the quantum side, I need a more compact algorithm. Okay. And after that, these two processes, it's trial and error. I just need to keep choosing different A's again and again and again and hope that I find an A for which R is even. And then again, hope that P and Q are distributed between them. So there is a game of chance, which is why the first step to Shor's algorithm, is this. First step is choose some k less than n. If n divides, sorry, if k divides n. Stop. That's it. So the very first step of Shor's algorithm is to just randomly try to divide by a number. So even Shor's like this is not a very definite strategy. There is a lot of probability that goes on in it. So it is not a one-shot algorithm like say quantum Fourier transform or something like that, where I just do it and I get the result. Or, as I'll be discussing, I'll also be talking next week. I'll be talking about the Bernstein-Maserani algorithm, where the answer is pretty cut and dried. If my quantum computer has no errors, I need to run the algorithm once and I will get the correct answer. Here, even if my quantum computer has no errors in it, if I have an error-free quantum computer, I'm still not guaranteed to get my answer in one shot. So this is a very complicated process. So we need to do this several times over. So although people will say, yes, Shor's algorithm has a polynomial time, complexity, the actual search, the actual effort taken to, factorize two numbers using Shor's is in reality very difficult. Okay. So now, how do I construct, a to the power r? How do I construct this? How do I construct a to the power r mod n? How do I construct this function? Because we need to know some example, right? So the example that we previously considered. So let me switch over to Qniverse. 7218 is still running. Doesn't matter. Last night, I already ran the same algorithm. So
Jotishwaran, you can click on that. Update will not happen immediately. If you click on that
okay.
job
No,
ID,
but
it will
nonetheless, I
update.
have a version where I've run the algorithm already.
Okay.
So the number 98 was used. So A was equal to 98. They tried it. Luckily, 98 was a good choice. They managed to find a period and they managed to get a factor. So factors are 11 and 13, as we just saw. Let me go back, since Santoshji mentioned that I should click on it. Let me click on it. Output is still processing. It's fine. In the fullness of time, this will also give me the answer. Okay. Now, how do I construct the wait, why is this not happening? Yeah. No. Yes. Okay. Yes. Now, let me take a very simple example. Now, this is almost trivially simple, but the number 15, this was the first number factorized by Shor's algorithm. So we now talk about some history. So by Shor. So this was factored for the first time on an NMR based quantum computer. So this was factored on an NMR based quantum computer. I think this was done in like the late 90s or early 2000s. I don't remember the year exactly. Based quantum computer. Now these NMR based quantum computers are no longer being used because they have severe scaling issues. So these are like, not even considered valid candidates anymore. They needed a total of 7 qubits to perform this factorization. So what will that circuit look like? So for that, let me consider 2 to the power r mod 15. What is that? This is actually relatively easy. R equal to 1, I know the answer for this is 2. R equal to 2, 4 divided by 15. Again, 4 is less than 15. So the answer is 4. Equal to 3. Still smaller than 15, it is 8. When I do r equal to 4, I will do 16. I will get 16. What is 16 mod 15? When I divide 16 by 15, what is the remainder? The answer is 1. So even here, again, r is equal to 4, which implies 2 to the power 4 minus 1 divides 15. So is congruent to 0 mod 15. So from this, I will get two factors, 2 to the power 4, 2 to the power 2 plus 1, 2 to the power 2 minus 1. So, right? Yes. So from that, I will see that I automatically got both the factors, because 2 to the power 2 plus 1 is 5, 2 to the power 2 minus 1 is 3. So this is, which implies 2 to the power 2 plus 1 into 2 to the power 2 minus 1 is equal to 15. And this number is 5, this number is 3. I will simply observe that 5 and 3 are both prime numbers, and therefore they have to be the factors of 15. So this is how the first prime factorization using Shor's algorithm was ever done. Now, how do I construct the oracle for this? So yeah, this I will also address this matter to the members of CDAC who are present here. Let me quickly go to the composer. So it can be done using, let me say, I choose a 6-qubit circuit.
Jotishwaran, sorry to interrupt. Can you
Yeah.
switch to the lighter mode so that it is easy
Oh,
for
yeah.
viewing?
Sorry.
No problem.
Yes. Where do I switch to the light mode? Like, where is it? Can you quickly?
At the top, next to the credits. Ah, correct.
This one? Yeah. Oh, okay.
Yes.
Cool. Okay. I thought that was some settings thing because it looked like a cog. Yeah. So 7218 has also run. Let us quickly look at that. See, now this is what I was meaning. This is what I was trying to tell you before. See, when I previously ran this algorithm last night, it shows 98 and got 11 and 30. But what has happened this time? This is good luck. We got the second case that I was trying to see. With A equal to 30, a trivial solution was found. A equal to 9, nothing was found. So it tried first two numbers. It did not happen. What happened is maybe both the factors ran into one of the two factors of 2 to the power r minus 1. So the algorithm did not conclude. Then A equal to 9 was chosen. Again, nothing was found because probably for A equal to 9, the R value would have been odd. So the algorithm stopped there. Ultimately, it shows A equal to 87, and then it was able to find the factors. So this is what I meant by Shor's algorithm. Even in spite of all its advances and quantum parallelism and everything, is still a randomized algorithm. I will have to pick a number at random, and it is just a question of luck. If I get a success, it is good. If not, it is what it is. So as you can see this, we didn't get it for the first two shots, and then finally for the third value, we were able to get the factors. Now let me move back to the composer. So let me quickly construct the circuit. So it's going to be this, and this, here. Don't ask how I'm constructing this. I'm constructing this because I worked this out yesterday. Okay, so right. And let me close this. I don't need this. This way I can zoom into that. And then I will need my text gate. And I need to modify the properties of this to go to another control. This Q1, make this Q5, and save. Then copy this. No, if I drag it, it will, or I can define it as a new gate actually. Don't expand. Oh, from a group because it's a single gate. And doesn't matter. I'll add these one by one myself. So I will change this to another control again Q0 and Q1. Set this to Q4. No. This save, and then this and this. So another one here. Edit this. Other control Q0 Q1. This goes to Q3. See this. You know what? I'll just close this up kind of. Yeah. And finally, I will have my last default gate, which goes to again Q1 down to Q2. Yeah, so the oracle will look something like this. Now, let me go back here and write the binary values. Okay. Now, R can vary from 1 to 4. However, I can also switch this around to 0 to 3. Like I can also write R equal to 0, in which case I will compute 2 to the power 0 mod 5, which is 1. So if I can show that this thing moves from 1 to 48, then we are proving our point. Okay. So R equal to 0, R equal to 1, R equal to 2, R equal to 3. This is the part that we will observe. Okay. So let me go back to the composer. And let me say now, initially, both like by default, these Q0 and Q1 are always 0. That implies the last bit should be 1. And we can observe that here. I think I can also close this. Can I not maximize this? But I hope this is visible on the screen. So as you can see, first 2 bits are 0, all the bits are 0, only the last one is flipped to 1. Let me say I want to pass 1, 1 to this. So I will put an X gate here, another X gate here, and the output that I'm observing is the input has become 1, 1. So the third bit.
Jotishwaran, can you hover
Yes.
on the graph? That will tell you the number.
Oh yeah, here, yes. See, you can see that it is 0, 0, 0, 1, 1, 1. Essentially, the first 2 bits are 1, 1, and the third bit, which is essentially Q2, the MSB of this. Like, let me also write the thing here. So this is, so let me in red write the binary expansions for this. 0, 0, 0, 1, 1, 0, 1, 1. And here we have 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, and 1, 0, 0, 0. So input and output, 2 bits, 4 bits. So that is my 6-bit string. In our visualization, the bit order is reversed because of the endianness of that thing. So you will find that when I made the 1, 1 thing, I have 1, 1, 1, 0, 0, 0, which is the reverse of this. See, I have 1, 1, 1, 0, 0, 0, which when reversed will be written as 0, 0, 0, 1, 1, 1. So this oracle that I have developed, this function that I've circuit that I've developed here is giving me the right values. Now, how do I get the list? How do I get the entire list here? I get the list by doing the following. I will replace these by the Hadamard. Yes. Now, if I come down, there are 4 peaks. First one is 1, 0, all zeros. So this is read from the right side. So if the first 2, my input bits are 0, 0, that is if the exponent is 0, then the last bit is 1. Here, if my exponent is 1, 0, then the second last bit is 1. If my exponent is 0, 1, then the third last bit is 1. If my exponent is 1, 1, it is 1, 1, 1, 0, 0. So I now have a function that gives me all the modular exponent values. Now, how did I compute this function? By observing this table and constructing the appropriate Boolean function. So this is a strategy, and there is an algorithm to do this for any A and N. So that process typically takes order n cube time, where n is the size of the number, essentially the number of bits in the number. So n there is not the RSA number n, I should say order b cube, where b is the number of bits in the RSA number. So it will take that much time and that much gates. So constructing the Shor oracle itself will take some classical processing. Okay, so yeah, that. Now, unfortunately, the CP gates that we have here. Wait, oh, I deleted it. Sorry. So the control phase gates that I have here. My God, is it getting? Yes. I am unable to add any control qubits here. So technically, after this, I will need what is known as a multi-control phase gate. I can technically construct that using single control phase gates, but the construction will become very large, and I cannot explain how I'm doing that here. And again, it will take a lot more time. I really wanted to construct this oracle end to end and show you that this is the circuit for Shors, and we are able to get the factors. But the circuit composer definitely has some limits. And had I coded it, I would be doing nothing different from the demo that is already present. I cannot go through the lines of codes and explain what is happening. So for today, I will have to be satisfied in showing you that it is possible to create a circuit that can create the list. So the circuit is, sorry. The circuit is this part. It is essentially everything in here. So this is my, I can group this and say this is E215, which is exponentiation of 2 mod 15. Let me say E2M15. Oh, with 3 letters possible. Okay, then let me say it is 215, 2 mod 15. And this is,
You can add more
exponent.
description.
Yeah. I'm writing exponent of 2 mod 15 or 2 to the power r mod 15. So, is it not saving? Oh, 215 is not good. Let me just write it as
the character,
will brackets work?
Yeah.
Okay.
Gate name, can you keep it as alphabet?
Okay, yeah, sure. So I will say exponent of 2 mod 15, yeah.
No, the gate code. Two instead of 215.
I will say it is. Well, I don't think there is an MOD gate. Let me just try this.
No.
Yeah, MOD is there. So I can just invoke this circuit, and there is a method to transfer the numbers here into phase factors. Sadly, its implementation is rather complicated with the presently available gate set on Qniverse. Maybe with further upgrades, whenever that happens, I will put up my own demo for the Oracle construction for Shores so that you can use it.
Jotishwaran, to update you, we are working on
No, I know. Like I've spoken with Henry, and he's been mentioning those things. So yeah, I'm just saying presently this will take too long, but in due course of time, the features will be available, and I will personally make sure that these demos are up here so that you can, not only run Shor's algorithm but also try constructing the various oracles. Like have a more hands-on, feel of the algorithm end to end rather than just call a function and run it. So that you can see how the circuits are being constructed. We may need to break some, change some limitations of this composer also. But in the fullness of time, we can expect to have all these things. So that is pretty much what I had to do today in Shor's algorithm. I see that I've overshot my time by 10 minutes. Can I please correlate this circuit with the RSA algorithm? No, I cannot. All I can say is I've constructed this function. I've constructed this function 2 to the power r mod 15 for 4 values of r equal to 0, 1, 2, 3. I've constructed that. And for that, I needed 6 qubits. So you can understand why the 7th qubit was needed to factor 15. Because typically we don't take r equal to 0. R equal to 0 is a bad number. I will start from r equal to 1 and see when I will get a to the power r mod n congruent to 1. So they needed the 7th qubit to see that yes, once I go to r equal to 4, 1, 0, 0, then I got 1 again. So the 7th qubit enabled me to do that. Why didn't I do it here? Because more than 6 qubits, we won't get the probability values. I would again have to run the circuit, and that would again take time. So I just gave you a very small toy example to show that this is how the oracle is constructed. Now, some parting remarks, just a couple of minutes. So let me just make a new slide and change the layout to blank. So what is the current state of affairs? RSA, now because of Shor's algorithm, like people say that yes, Shor's algorithm made RSA invalid, it is no longer safe. But that is actually not entirely accurate. RSA 250, which had 829 bits. So here 250 is the number of decimal digits. For some reason, they keep mixing this. Sometimes they write the number of bits, sometimes they write the number of decimal numbers. It's, annoying. So this is decimals here. Okay, so RSA 250 was factored classically in 2020. This is the primary reason why people are moving towards post-quantum public key cryptosystems. And also, elliptic curve Diffie-Hellman was broken. So these are the reasons. Quantum attack is not the reason why people are moving to post-quantum cryptography. There have been legitimate classical attacks that are breaking these systems in 2020. You can look this up. There is a paper, they used 2,700 CPU cores, a lot of memory, and classically broke RSA. Okay. Now, where do we stand on Shor's? The largest publicly known number factorized by Shor's algorithm. So, largest number. In case you don't know, prepare yourself to be surprised. Largest number factorized is, drum roll please, 35. That is where we are. 7 into 5. That is the best any existing quantum computer has been able to achieve. Additionally, another thing that has been proven on an error-prone quantum computer.
Shor's algorithm, no, can't we factor 1023 in our simulator?
On a simulator,
On
yes, we can. I'm talking about a real
simulator.
quantum computer.
See,
On a large enough simulator, yes, we can factor, significantly. Like, see, that isn't, we can, I mean, technically speaking, we can go all the way up to 829 bits.
right.
Because it is a classical computation. So if I have enough compute power, if I can, structure and build my system correctly, parallelize routines, then yeah, I can go all the way up on a classical machine. What I'm talking about is the quantum computer, which is the also great threat to classical crypto systems. Like, it is important that we understand what kind of a real threat they are. On an error-prone quantum computer, QC, Shor's algorithm is guaranteed to fail asymptotically. This is a very strong result. Like, if I have a quantum machine which has errors in it, then I can always find a large enough number n which the computer cannot factorize. Asymptotically. So that is
How
what
about
failing.
the latest IBM's quantum computer of 156
We don't have any
qubits?
public data on that. Publicly, the largest number factorized is by the IBM machine, and that is 35. This was done in 2022.
Okay.
They haven't revealed anything. I'm sure privately they have moved ahead, maybe gone to some 3-digit numbers.
Okay.
If we are believing only the publicly available data, what they are doing in classified environment, we cannot comment on it. Fun fact about RSA. RSA stands for Rivest, Shamir, Adelman. I'll just quickly write it here. So the names of the 3 people who came up with the system: Shamir and Adelman. So they came up with this, I think, in the late 70s, 1977 or 1978. That is when they came up with this crypto system. In 1997, the British, intelligence organization, GCHQ, I think, General Communications Headquarters, revealed that 6 years before this, in 1971 or 72, one of their in-house scientists had already developed the same method. And they had been using RSA like 7 years before it was private. That information was declassified in 1997. So what is happening in the classified environment, we can never comment. But I'm just talking about what is publicly available. So that is another reason why we should treat quantum computers as a threat. Practically, we are seeing nothing. So we cannot say, okay, nothing is going to happen, because behind closed doors, people might be doing a lot. Although the probability of that is on the lower side. Like, with whatever experience I have, I can state that. Okay. And final thing is about, yes, if I want to factorize RSA 2048 using a quantum computer, so I cannot use an error-prone quantum computer. I need a fault-tolerant quantum computer. I need some error correction code set up. So if I want to factorize RSA 2048, people have been performing estimates for this over the years. The most recent estimate we have from April of this month. So that will say require something between 6 to 6.5 million qubits, million physical qubits, with appropriate connections so that I can run surface codes to correct the errors on it. So that is the present, like, experimentally or rather theoretically estimated gap. We will need 6 to 6.5 million qubits. Okay. So Yeah, so this is the state of the art, state of the affairs on RSA and similar systems. One thing the main thing that I wanted to tell you is, like, if somebody is thinking about post-quantum cryptography here, the reason why we are going towards post-quantum cryptography is not because of the quantum computer, it is because of actual classical attacks that are breaking the
Okay.
existing, crypto systems. So people are moving to, lattice-based systems, LWE, LPN-based systems, and so on and so forth. But word of caution, again, they have the same problem. They have overcome this. They have created crypto systems which have an exponential time complexity to break, but again, they're not proven to be NP hard. So even now, we are not using any true NP hard problem. With an NP hard problem, we can believe that even a quantum computer will not be able to break it. Right now, we do not have a single proven NP hard crypto system that is being used in any standardized, encryption schemes. So that is still missing. So whatever post-quantum crypto systems we may have, if we do enough studies like this, essentially like this, if we study the algebra of the structure, if we study their nature, we may still be able to come up with potential quantum algorithms that can break them also. Which is why, yes, we are studying quantum computing, that is very important, but it is equally, or if not more important, to go back to the roots, understand the algebra, understand the structure of these objects, and look at the fundamentals, because that will give us the ultimate insight. We need to construct the algorithms which will break the upcoming systems, and it will also give us guidances on how to create truly safe crypto systems. Yeah, so
Right.
with that, I finish my session today. Really sorry for
Yes.
overshooting my deadline.
Yeah, no issues. It was a very uh, deep insights into RSA and Shor's algorithm. Thank you very much, Jotishwaran, for accepting our invitation and
It's a pleasure.
presenting in this webinar series. We look forward to working with you in more other
Yeah,
algorithms
yeah,
and
by all
uh,
means.
collaborative development aspects.
Hmm.
Uh, there is one question. Can you take this up?
Yes. Yeah, sure. How much of the so regarding the there was one question before this asking about
Yes,
practicality of quantum computers in the next five
correct,
years.
correct.
I actually, can't comment much on this because a lot of work is going on in a lot of different directions. Like, again, this is hearsay. I've heard from people that, many of the bigger powers there are focusing into material development now. So they are presently, pausing or reducing the amount of money they spend on making the existing quantum computers larger. But they are going back to the roots and constructing different materials, which may allow them to develop better functioning qubits that are more resistant to noise, that are easier to interconnect and develop. So if we get something there, then in the next 5 years we may see a huge amount of growth. If nothing happens there, if we are using only the quantum systems that we publicly have available now, then in the next 5 years I don't expect things to change much, like in terms of like threats. Like Grover's algorithm is not going to be able to break AES 128 or 256. Shor's algorithm is not going to be able to break any RSA. It probably is not even going to be able to break RSA 250. That has been classically broken. So
Yes.
it is going to be pretty much status quo for the next 5 years. But if we have some development on the material side, all of that can will go out of the window right away. And people sometimes make claims, like in sometime last year, Microsoft made claims that they have created a new state of matter and whatnot, but subsequent to that, there has been no follow up. Most of their claims have been refuted, so they've kind of gone quiet. 3 years ago, Google did the same. So sadly, there is a lot of this hyping business also going on. That is never healthy for practicing science, but it is what it is. It is the world we live in. The other question was how much of these claims are correct. Would take so many years on an ordinary supercomputer, but the same would be solved in a few hours. If I have, so to answer your question, if I have an error-free quantum computer, these claims are true. On our practical quantum computers, it is almost guaranteed that not only will they not work, they are guaranteed to fail. You can prove that if I have enough error accumulation, any algorithm, any quantum algorithm that you can think of will just become a pure source of randomness. What comes out of there will be completely random. You will get no information from it, no answers from it. So again, sadly, these claims are, what the CEO of Microsoft made this claim that you just mentioned. in a press conference to the entire world, he just said that, yeah, the thing I'm holding in my hand is more powerful than any supercomputer on Earth. Well, but if he was being scientifically accurate, he should have said it has the potential to become more powerful than any supercomputer on Earth. Sadly, people don't want to like caveat their statements, don't want to make things because it is not a very sorry, it is not a very bold claim. Like it doesn't turn heads, it doesn't grab headlines. So people
In
try
fact,
to push more towards.
Google
Yeah,
also
Google significantly
showcased
before
only
that they
the
claimed that they've achieved supremacy.
yeah the only
And
the
like in two,
randomized circuits, not
yeah,
actual
yes.
any use
No, but
cases.
pretty soon the one algorithm that they did claim to solve was solved on the, a single node, the classical computer by a bunch of scientists, and that was also published.
Yes.
So like it has been rebutted, and these things happen. So any other questions? Hardware as
Uh,
quantum computer, what do you think as? So the thing is, I'm very, so this is a question by Rahul. I'm actually very biased here because for some reason, now again, I'm not saying I'm right. For some reason, whenever I look at AI and ML, I have this weird feeling in my stomach and I'm unable to study that. So there is a reason why, in spite I've been around computer science departments almost all my adult life, I've never been able to study and something just seems off in my head. So while I know what is happening there, I've never been bothered to understand what's happening there. So I cannot make any accurate comments here. But what I will
okay.
say is quantum computers as themselves, even regardless of AI or ML, if I have perfectly functioning quantum computers, there is a huge amount of benefits we can gain from. So for
Yeah.
so last week you were introduced to quantum phase estimation and quantum
Yeah.
Fourier transform. Just that, because Fourier transform is one of the best available analysis tools we have. If I have a machine that can perform Fourier transform fast, then that will make a lot of things easier, and it will make a lot of computation and analysis in like countlessly many areas stronger.
I would
So
say the current quantum computer is of 1960s classical computer.
you know what? I can't even say that because on a 1960s quantum computer, I could run a scaled down version of my problem and still get the correct answer.
Okay.
Like the 1960s quantum computer
No,
had
not
Hamming's
quantum
error correction
computer. I
codes.
meant
Sorry, classical
classical computer.
computer had
No, I
Hamming's
meant
error correcting codes inbuilt into them. Richard Hamming introduced that in World War II itself. So the tape tech computers had error correction on them. Our
right.
present day state of the art computers don't have inbuilt error correction. So we have not even approached that. In my humble opinion, we are, in the level of building transistor circuits and, building individual logical circuits and things like that. That is more or less where we are. Now,
Okay.
yeah. Yes, there are these harvest now ideas also where people will say that, yes, I will, collect and keep all these data. And when I get a quantum computer, I will do those things. But unless and until I, have a meaningful time scale for this, any harvest, like that is the thing, collect now and track later kind of a situation may not work. So Swapan Kumar Nandi, I think we are meeting again. I think I've met you before on one of the CDAC courses. So I don't like, yes, it is a credible threat, but how practical it will be, I do not know. What about QKD? Is it protected against quantum attacks? Well, with QKD, it is possible to have classical attacks. We can have classical denial of service. We can have, plenty of things we can do where we can simply disrupt the QKD system.
Right.
QKD protocols are actually very good, but there are many what to say, like attacks where I can tamper with the system, because ideally we are aiming to have some kind of a free space communication that comes with an advantage and a disadvantage. The advantage is, yes, now I can perform secure key exchange very easily. The disadvantage is anybody with something as small as an electromagnetic transmission antenna can interfere with your photon streams. So again, QKD is a very encouraging, avenue to look into, but ultimately in the long run, and considering that how modern day telecommunications are growing, like with 5G, the number of towers has kind of quadrupled or doubled. As we go further, this number only seems to be increasing. So the intrinsic electromagnetic noise in the atmosphere is also likely to increase. So in that case, I don't know how good free space QKD will work. Now, if we are not doing free space QKD, if we are doing QKD using a quantum channel, then people will start targeting the quantum channel. They will just, drop a bomb on your optic fiber cables, and then you don't have QKD anymore from a very practical standpoint. And these days we are seeing that it's happening. So any other, we have, can we tell today's similar to, okay, so this we have already addressed. 6 million, do you imagine or see Shors running only on superconducting qubits or what, or is it possible somehow to translate Shors on? Again, I do not know. I do not know. Will we be using these materials, or will we have some entirely different implementations of a quantum computer, of a qubit, and things like that? I do not know. Like, if you give me a qubit system, I can study it and tell what's happening there. But if you ask me, can I guess what is going to be the next standard qubit, hardware that we are going to fabricate our qubits on, and what kind of an architecture it is going to work on? I do not know, because the research avenue there are wide open. So
True.
yeah, that is that. I think we've come to the end of the questions.
Yes. With this, thank you very much, Jotishwaran.
Yeah, thank
It
you
was
for
a
giving me the
very
opportunity, and I hope everybody who attended also had a good time. I'm sorry, like, we've taken a little bit more time, but I hope we
yeah,
had a good discussion.
nevertheless, it was a very informative and deep dive into the
Yeah,
algorithm. So
yeah, I
I
wanted to
think
ask just
participants
one more thing
also,
before ending.
yes.
The recordings of this session, will they be uploaded somewhere, or?
The recording of the session is will be available in our channel,
YouTube channel.
Qniverse.in YouTube channel.
Oh, wonderful.
It is
Wonderful.
available. Yeah.
Great.
So
Okay.
participants, those who are not able to attend the session for some
Okay, they
reason,
can attend from there.
they also can go through the video sessions. Yeah, and it was a wonderful talk. Thank you very much.
Yeah, we got one
We
more
will,
question. What I
yes.
will say is, since I'm showing up next week, I will address this question next week.
Okay. Thank you.
Yeah.
So
All right.
yeah, we will meet you next week with
All right.
Bernstein-Maserani algorithm. So
Yes.
participants who want to refresh their learnings before coming to the next session, you can go through the Bernstein-Maserani and come prepared for a lot of questions. And
Yeah,
I
by
think
all means,
Jotishwaran will be
I'll
happy to
welcome.
answer all those questions.
Yes, yeah, more than happy.
Yes, yes.
Yeah.
Thank you very much.
Yeah.
Thank you all participants.
I'll see you again next week. I'll
Yes,
stop sharing.
bye.